Hi, welcome to tutorial 6.2 part 3. We're going to kind of take up where we left off last time. The only difference will be that this time we're going to actually calculate out the velocity of an ejected photoelectron. So nothing else is new, it's just that you're trying to keep track of all these kind of conversions and steps at the same time. So it gets a little bit hard to get your bearings, so let's see if we can understand it. The question here is: a sample of gold metal is exposed to light. The work function for the metal is 5.3 electron volts. That's what it takes to knock that electron off of gold. The question is, what's the velocity of the resulting photoelectron if the wavelength of the incident light, this light coming in, these little blue dots are supposed to be chunks of light, if they come in and they have a wavelength of 170 nanometers. So what we're going to have to do, we're going to have to try to figure out how much energy each of these little chunks of light has, how much energy then is left over after we remove the electron, and then figure out what the velocity is of the electron after it has that much, with that much energy. Okay, so two steps here. First of all, the electron volts have to be turned into joules, because we're going to end up with a joule value when we get the energy for this photon, and we have to come up with that energy. How much energy does this light have that has 170 nanometers as its wavelength? So the first part, getting the wavelength into meters, we have to do that because in order for us to figure out the energy, I need to know actually the frequency of light. So the first step is to say, if I get these nanometers into meters, I can divide into the speed of light to get the frequency. So 10 to the 9th nanometers per meter, I divide 170 by 10 to the 9th, that leaves me with 1.70 times 10 to the 7th meters. That's the wavelength. Next, I'm going to take that now and divide that into the speed of light to figure out the frequency, because I need the frequency to get at the energy. So here's what we've done lots of times already before. To find the frequency, I take the speed of light and I divide by that wavelength that we just found. Those little blue dots have this wavelength, so they have this frequency, 1.76 times 10 to the 15th waves per second. Okay, good. I have the frequency. I'm ready to go ahead and get the amount of energy per chunk of light, per photon, by multiplying by Planck's constant. Here are my numbers. The energy per chunk of light is given by Planck's constant times the frequency. Now this number, Planck's constant, make sure you put that in your calculator so you don't have to remember it. 6.626 E negative 34 when you type it in your calculator, just so you're not constantly futzing around looking for the number. In any case, multiply by the frequency. These two numbers. This was the frequency we just got from the previous part of the calculation. And I now have the energy that we come in with, 1.17 times 10 to the minus 18 joules. Each little chunk of light delivers that much energy to that electron. Alright, how much does it take to get the electron away from the atom? Well, I have it given in electron volts, 5.3 electron volts. I first have to figure out what is that in joules. I multiply by the conversion factor. That's 1.6 times 10 to the minus 19 joules per electron volt. Again, might be good to store this one in a calculator or just remember the number, whichever is easiest for you, so you're not looking around so much for these values. In any case, this is the amount of energy, 8.48 times 10 to the minus 19. That's the energy required just to remove the electron. Okay, I come in with this much, 1.17 times 10 to the minus 18. I need this much, 8.48 times 10 to the minus 19, to remove the electron. What's left over, I just subtract the two. 3.22 times 10 to the minus 19 joules. That's left over in the form of kinetic energy. All I have to do now is say, well, if you have that much kinetic energy, how fast are you moving if you are an electron with a particular mass? Here's our kinetic energy equation, 1/2 mass times velocity squared, and the mass in question here will be of an electron, because that's the thing that has the kinetic energy. I solved it here for v squared instead of for v, just so that the square root sign wouldn't make it look too imposing. So we multiply 2 times the kinetic energy and divide by the mass of that electron to get the square of the velocity. So 2 times the kinetic energy we just found, divided by this number down here, which is the mass of an electron, comes out to 7.07 times 10 to the 11th meters squared over seconds squared. So now when I take the square root of this number, I get the speed, and that's what we're after, or the velocity, 8.41 times 10 to the 5th meters per second. Okay, so these problems are all very much the same. Sometimes you're asked to move in one direction, like you have to find the velocity if you're told the wavelength or the frequency of light that comes in and the work function. Sometimes you have to go the other direction from the velocity, work backwards and figure out what kind of light must have been absorbed in order for this event to take place. But in either case, it takes mostly some practice and kind of facility, just getting used to your calculator, making sure that you can type the numbers in without making a lot of mistakes, and do so pretty efficiently so you're not just bogged down with minutia, but can actually kind of understand what's happening. All right, we'll practice a few of these in class. We'll kind of type them in together in the calculator so we feel comfortable. Great, see you then, bye.